Okay, so we're going to continue our little Welsh algorithm example here, and that's I think we're going to the last time we're going to work on that. Next time we're going to have a look at Rust and CEO. It's because it's also to answer some need of the project. There's a need to do some GLAO simulation for system engineering. So we're going to use CEO with the Rust framework to try to set up that. So that would be a good way to learn that too. But let's finish this little exercise here with the Welsh algorithm. So I learned a few more things in Rust. So the last time we looked at a bit the concept of borrowing ownership and lifetimes in Rust. I don't know if you have any question about that. If not, let's get other aspects of Rust. So in the algorithm, so in the Welsh algorithm, so there's to compute the power spectrum, we left something aside that all other algorithms have is you can usually specify a window that you're going to multiply the signal with divide or signal in overlapping segments. And all the Welsh algorithm usually multiply this segment by a window, which is going to taper the end. Otherwise, you're going to have some discontinuity at the end. And if you take the discrete Fourier transform of that, that gives you ringing, high frequency ringing. So all algorithms have by default, all Welsh algorithms come with a window to do that. So we're going to see how to implement that in Rust in a way that the window we can either provide some or the user can define it. And we're going to see how the user can come up with its own windows, because if you look at the windows, I don't know if it's that in the Python. Okay, the windows. There's a lot of windows available. Or window, yes, I think you see that here. Windows. Desire window. I didn't give you the list. Here. Yes, you see, you can have a lot of windows. I'm not going to implement all of them. So we can implement a few of them. They have some default. Oh, Christophe was able to join us. We were just starting, Christophe. I was a bit late to get to start. So we're going to maybe implement one or two and let the user decide to what he wants to use. So let's see how we can do that with Rust. So let's see what we want to do first. So if you remember, it's here that we are segmenting our signal. Right, so here we take our signal and we apply the Windows iterators, and we get our segment here that we convert to a complex number. So what we really want to do is that when we get with signal, we want to multiply the segment variable that we have made. The segment variable here by some weights given by the window. So basically what we would like to have at some point, but we're going to write it here for now, let weight have some weights. Let's weight equal, let's start with something with all 1 to start with. So we need a vector which is the size of the segment size. Segment size. Like that. And we want to multiply the segment by the segment, yes, by each by the weights. So you can do that also with the iterator very easily if you zip here the weights. That's something you can do with the iterator. So let's see what's happened here. So remember that after the Windows iterator here, it's what gives us our segments. Okay, and so we have at the output of that we have a vector of n size or an array of n segment size. Our weights are also n segment size. So if we zip two iterators together at the output, we get in fact a tuple. It's what you can see the type here that my editor shows. Now I have two arrays of the same size. Okay, but the tuple by itself is not very useful, so you can directly deconstruct it like this, where you get the segment array and the weights array. And so we have one element of each array, right? And so we can just, we have, am I doing the right thing? No, I'm not doing the wrong thing. The zip should not be there. The zip should be here because I want to, yes, that's what I want to do. Here I have the, yes, that's the way to do it. Here I have, like, voila. So, at that step here, I have an array. And I want to go through each element of the segment array and each element of the weight array and multiply them element-wise to apply the window weights to my function. And you can see that now I had only a reference to one element before. Now I have a reference. I have a tuple with a reference to two elements, one corresponding to segment and one corresponding to weights. So now we can do something like that. And then having, oops, x equal w. And that can give me what I want.
What's the meaning of the square brackets? For
here?
segment.
This one here? Yes. So that means that the segments is a slice. So that means it's kind of a reference to an array.
Oh, okay.
The signal is original. The original signal is a vector, and the Windows iterator here take a slice into it. Really a slice.
Okay, like a subset.
Like a subset of the signal.
Okay.
Okay. So we get that here, and then I created a weight vector, which is the same, which should be self. Self, so the same size as the segment. The same size as the segment, and I zip. So I create an iterator on segment here, on the segment, and I zip it with an iterator on the weight, and that gives me an iterator on a tuple of one element of segment and an element of weight. But I collect here through the map by deconstructing the tuple, and then I can multiply one by the other. And that should compile. That makes sense. Yeah, that's okay. So of course here, so that's the way you can weight your segments. Of course here we pass the weight directly in this function. In fact, we would like that to come from either a definition of the weight we set or from a user-defined thing. So a very simple way to do it For example, we could define a weight vector here. And like that, and here we could just pass a vector out of weights to the constructor of our well structure, and define and plug and have it here, set it here, and then we won't need that anymore. Okay, and we can just have the self weights here. Yeah, that compiles too. So that's one way to do it. Can have the user to pass the weight, but here you force the user to always pass the weights of the window into your constructor, whereas you would like to be a bit more generic than that. You may want to have some default weights, or even have a default structure which computes the weight, or things like that. So instead, you could also pass a structure, which we call it window. We could call it one. If I define a structure here, struct one, which contains, for example, the weights as a vector of F64. And then we could, instead of passing a vector, we could pass in the window for one. And in that case, the window will be one. A function, you can define a function new on that one. For example, one. One.
Rod, this might be a stupid question, but in Rust, is a structure similar to like a structure in Python, or like a dictionary in Python?
It's closer to a class in Python.
Class, okay, thanks.
But there's no the same object-oriented properties than in Python. It's inheritance. There's no inheritance like in Python, for example.
Okay.
To add another constructor to Welch, would you just create another function that turns a self, like the new?
What I'm doing now, I'm creating a constructor for one, the structure one. I can barely hear you for some reason, so I hope I understand the question correctly.
Oh, I didn't have my microphone in front of me. It was like way over there.
Okay, that's why it was a bit difficult to.
Yeah, I was just wondering if you wanted to have like another way to create a Welch, maybe that uses a set of default values or something like that. And you can have multiple constructors, right? Like
yes.
You could have a new too.
Yes, you can do that. Yeah.
Okay. And it's just you just add another function with the same inputs, outputs, or different inputs.
Yes.
It just needs to return a self, and that's that.
Yes, there is a programming pattern called a builder pattern that is useful for us to create constructor, which so Python, for example, has this notion of keywords that you can pass to a constructor. There's no such thing in Rust. But what they call the builder pattern, I may have a session on that at some point. You can get something very close to that. So you have still a single constructor, but you can add kind of keywords to it. If they are not keywords in the Python sense, but we can do that. Okay, so here I'm creating my, that should work. And well, it doesn't work because here we want to wait. So we could also create to be very not too specific as a function to create weights. We're talking about slice. So here I'm returning a slice by returning self.weights.asSlice. So it's really kind of a pointer to the whole vector itself. And I know I can I should be able to do something like that, where I take my window structure that weights. What? Ah, yes. Okay, as usual, the constructor is right, we should be good. Yeah, it works. So this is another way to pass a weight is by passing a structure, which and use the structure constructor new, which is rather standard in use, but rather standard in Rust, but not everybody uses new. And we use the function weights to retrieve the weight. Does that mean with that, the user could define his own structure and try to pass his own structure, right? So, and that should, if we go back to the example, I should set up differently here. It's going to be nice to be. Yes, let's set up this as like this. Like this, we can have this as the example together. Example. Welsh. So like this, our function doesn't have, or our structure doesn't really have to reside in the library. Or we can put it in the example directly here. But you see the problem that and we can try to pass it to the constructor. Where is that? Ah, here. So here so now we can specify the one window, right? So, and here it doesn't work. So let me explain what happens. So when I add the structure one inside the library here, the library, when it compiled itself, was aware of the one structure and was finding the constructor new, the weights function, and so on. When we move to the example, if we compile the library, it cannot find it. It cannot find the structure one anymore because it doesn't exist in the library anymore. So, but even if we could try to compile the example, cargo build example Welsh, it doesn't work either. Even if the function one is defined here and we're passing it to the constructor which expects the one functions, the library has to be able to be compiled independently of the example. So that's why it doesn't work. So that's why what is going to be useful is the idea of the concept of generics in Rust. Yeah. When you want to pass two to your application, or to your library, in that case, a structure that can be user-defined and doesn't really exist yet in your library. So the way you do that in Rust, it's quite nice. So it can be, it's a concept of generic. So the window type can be generic, so it's a placeholder for whatever. So we're going to call it W, and then we're going to class it here with our lifetime. This is telling the compiler that we don't know what the type of this structure is going to be yet. It can be whatever the user decides, right? So the type here will be W2. Okay, but that doesn't compile yet because now we're trying to use this function here on the type 1. So we're going to replace that by the type of placeholder type or generic type W here. And then there's a problem because the compiler say, okay, we have defined the generic has to be present at the definition, and we need to replicate here when we implement here W and W here. Okay, so now we have a placeholder type for our window, but we're calling function already on this window, and so we still not define the library. So the compiler is confused. Where does that come from?
Rod?
Yes.
A question related to that. We have in the segmentation function code to handle the window, but now it's a placeholder, so it's not able to know what's inside of the window.
Inside
So,
W, yes. Inside is here. You mean in the window here? Yes, because that's why it's failing.
Okay.
So that's why it's failing, because it's a placeholder. It doesn't know. So when you have a generic that you want to use specific function on that type, that means that you need to constrain the type, and a bit like we do on GMT, or when we design something, we need to put requirements. You need to put requirements on the generic, and the requirements are this function, this type, must have a method called new that takes as argument input a usize and return an instance of itself. That's the first requirement. And the second requirement, you need also to have a wait method that returns a vector of double precision floating point. So we need to write this requirement for the compiler to understand why W can work with the application. Otherwise, W is too generic in that case, and it has no constraint, no requirements associated to it, and it won't happen. So how do you write in Rust what I just said, the requirement on W? The Rust has a more elegant term for requirement than what we use for requirements that we use generally. We use that traits. A requirement is called traits. And I think we should put a request at GMT to rename requirements traits. It's much more elegant, I think. So we're going to define a new requirement, a new trait, cube trait, and we're calling that window capital to define. So what we said we should add. The requirement is to have a method called new that take as input an argument, an integer of type usize, and return an instance of itself. Okay, that's one of the requirements. And the other requirement is to have a method called waits from the object itself, so from a reference to the object we're going to use, And this one has to return a vector of double precision floating point. That's how we write requirements in Rust. We call that traits. But that's really a constraint, or sometimes called a bound on the generic. And now we just need to tell the compiler on which generic. In GMGO, we'll say on which subsystem and at which level of this subsystem we're going to apply the requirements. In the rest, it's on which generic. We're want to apply that on W, so we just bind it, the requirement to or generic like that. And if you look at the compilation, it failed, but I will tell you what. The threat window is not applying for W. But I forgot. Yes, because I need to specify that both is definition and in the implementation. Here, I don't think we need to repeat here. Yes, and I compile the compiler. So you see, we have a generic type. The compiler doesn't know yet what it is, but he has all the information to allow you to continue. It's okay. Now I know that when you're going to create an application with your library, the user has no other choice than providing me a structure that implements this requirement, these traits. Otherwise, I will refuse to compile that application. Does that make sense? There's some nice logic behind that. I kind of like that. And it relates really to the notion of requirement you have with GMT. You have a placeholder and then you constrain it with some traits. So now what happened on the user side in the example? So going to the example, we need to make available our requirements to the user. So we need to import them. So we import not only the library, the wedge library, but the wedge structure, but now the window itself. And because here it looks like we almost have everything. If I try to compile the example, it's going to fail. Yes, it's falling. And it may sound strange at first, because on the library side, we define for the controller, we let the controller aware of everything it needs, and on the user side, the one structure you're passing has defined all the function you need, and we pass it here in the constructor of Welsh. Where is it? Where is it? Welsh. Here the function one is passed, right? So it seems that we have all the bits and pieces and still not compiling. It's because the compiler is a bit pedantic. He really wants you to be very intentional. So you really need to be intentional and telling, yes, I implement one, but the method of one I'm defining here are not something I made up. They're really coming and imposed to me by the library. So I need to say I implement, in fact, Windows for one. So it's really, like this, it's become obvious that which requirements you're going to apply to your system. So if you do that, and we try to compile our example again.
Sorry, Rod, I don't understand why you added the 4. Can you explain that again?
So it's just to tell the compiler that this method are related to a given requirement or a given trait. They are not something you made up.
Thank you.
It's something that you have to use. Yeah, it's method that you define because for your application to work with a Welsh library, you need this method on your structure. It's a requirement that you need to comply with, and you need to be explicit with the compiler to tell which requirement you are complying to.
If you wanted to add a method for one that was not part of window, would you still put that in the same block, or does it have to go in a separate?
You will create a new one like this. Implement one like that, and you create your next one here. It's a different block. because if you put it here, the compiler complies that the method you put here is not listed in the window requirement.
Okay.
It doesn't exist there, so you need to put here.
And can you have a default implementation for window?
Yes, absolutely. Absolutely.
And that would go in the trait?
In the trait, yes.
Okay.
So you can have a default. So here we keep it in the trait. Here we keep it in the trait. Here we see we just specify input and output, but you could write the full function, and it will be written here. And I think you can even overwrite it afterwards. If you say, okay, no, the default is not what I really need, you can overwrite it. So you can provide a default and overwrite it too.
Okay.
And so.
So the alternative would have been you just have the window struct defined as part of the library, and then anybody could create a window. But this way it's more flexible because people can create their own windows that
Yes.
have more capabilities.
Exactly.
And they still work with your library.
Exactly. Right. Let me try to. Doesn't want to compile. Ah, yes. Okay. Because we need. Ah, yes. Here, what I'm doing here, I'm passing the type. But in fact, I don't need to pass the type at all. Let me explain why. You see in the application which is compiled here works fine without passing it. It's because the compiler has really all the information. It's here where it creates a new instance of the window based on the definition in the trait, and then you use it here in the segment here. When here self window weight. So you don't even need to pass your structure now.
Can the trait contain variables? Sorry.
No, traits are just a functionality. So it's an important concept in Rust that is different from other languages. It's the separation of function and data. Structs really are there to hold data. You can also define method, but the main intention is to hold data. And on traits, you define functionalities that you can even share for others. As traits, like requirements, can apply to multiple subsystems or multiple structures. So you can share them. But traits are only for functionalities, to define function. Common traits, common function. So you see here, we don't need to pass it. Right? So how do we let the Welsh functions, which type to use? We just need to specify the name, replace, you know, in the definition, we have W as the generic type for the structure. Now we can just replace that with the concrete type, which is 1. We don't even need to define it in the application because we have provided a constructor in the requirement that has to be defined in the trait, and this one is going to use by Welsh. Let's see if I can compile that. Yes. So you see I did a little mistake. That's interesting. I define my function weight with that output here. Okay. But in the trait definition, I define it with another, which is a vector, not a slice. So immediately the compiler catches that and say, okay, there's a mismatch between the requirements and your implementation. You know, you're not compliant with the requirement, basically. It's what we say in GMT. Your design is not compliant. So here, as we usually do in GMT, we don't change the design, we change the requirements. That's what we do. We fail. So let's change that. And that should work.
The presentation is being recorded, right?
Oh my goodness. I should stop making joke about GMT. Thank you, Rodrigo. Building it taking some time for some reason.
So if you wanted to, because I want to create something so that has always an X and a Y and a Z property, like positions, translations, rotations. Would it make sense to kind of have a trait for all of these? And then how could I somehow make sure there's always an X and a Y and a Z, like using like a getter function or something like that? Or is that just not the way to do it?
You can. So the trait doesn't constrain the variable. You just constrain the function. So what you do with X and Y and Z. So if you want your other application to always, so yes, you can define a trait to get X, get Y, get Z. And I would have to see the application to understand a bit better what you mean by that.
Okay. What happens if in your trait you have a function that uses the properties X, Y, and Z of that struct? Can you do that?
Well, it's what we just did. If you look at the, if I understand correctly.
Oh yeah, because it always has the if you had a default implementation.
If you have a default, you can't use that. You cannot do that because here the definition of the trait, it doesn't know what self is, so you cannot use the properties. But when you implement it, of course, you implement it on a concrete type, not a generic type, and then you can do that. You can't use the property.
So that limits what you can have for default implementations, right? As a trait.
Yes.
If you cannot use any of the properties, then
Yes.
there's not a lot you can do by default. Okay.
No. You need to redefine your function each time.
Okay.
Okay. And here we are. It compiles now. So let's go through that one more time because it's an important concept. And there's something very powerful in Rust when you combine generic with traits. So we wanted to let our user to have the possibility to come up with their own window function. As long as they provide a constructor for this structure and a function called weights. We return the weights that we can do. Right? And so we encapsulate this kind of requirements into a trait. It's the equivalent of a requirement. And then, on the user side, we define a structure here. This is going to be our window of 1. And then we implement this trait on that window. And when we call now Welsh here, we don't even have to pass 1. We just need to tell the compiler that instead of W, now you're going to use 1. So it's a process called monomorphization in Rust. where so we have a generic code, and we have a library, and we have part of it is generic. The compiler doesn't know yet what it is. It just knows the functionalities associated with that generic that need to be present for the code to work. And in the application, when it compiles the Welch example, it's going to find, okay, now we have, instead of W, I need to use 1. 1 is defined, so I'm going to take the library and compile it with taking the piece of 1 I need and plug them in the code of the library where I need, and we regenerate. So for example, if we define 10 windows, when the compiler does its work, at the end, you will have 10 versions of the Welch structure, each with a different window. It's how it does. So that creates a bigger code, but there's no penalty in terms of computing time, because there's no if then else, for choosing the function. It will know exactly in the assembly code which one to use. So that's very powerful, this process of monomorphization of the code. Does that make sense? Any questions?
I would have just a comment. When you create the trait and when you use that in the structure in the library, it's a trait, but the syntax is the same as when you are passing a type. So I don't know if you agree with me.
So you're saying the syntax of the trait?
No, when you use that. So when you in the library we have the structure Welch.
Yes.
And when you say that it depends on the trait W, which is a trait, the syntax seems to be that you are passing a type.
Yes. Yes. In fact, the type is W, window is a trait. Window just defines the set of functionalities that this type must have to work with the library.
W is the data, right? And window is the trait.
Yes.
But the syntax is the same as window could be a type.
No.
In terms of syntax, not in terms of this.
No, because they use W, not window, for the type.
Okay.
Window is only up here above, here the definition, and here where we kind of bind traits to a generic type, bind the requirement to the type. He knows when he finds a function that is required for this type W, he will have kind of a table, and in this table he will say, okay, W as a trait called window. Can I find this function in window? And if yes, then he will compile. Okay. And the same on the application side.
I made this question because one of the difficulties I have when I'm reading Rust code is to recognize which kind of thing is what I'm looking at. So, okay, yes. It's a trait, it's a type. So that's what is one thing that is tricky when you are a beginner.
Yes.
To understand what kind of instance or what kind of thing you have at hand.
Yes. Yes, it is not straightforward at the beginning to read Rust code because of the mixing of type and trait, and then understanding the syntax takes some time. But I think you can see a bit how powerful that can be to create code that is quite generic, and then you specify your requirement and your traits, and then you bind that together. And this is a relatively simple example, but you can write quite more even sophisticated trait to implement some of the logic of your code behind. So that's quite powerful. Is there more question about that?
Yeah, I have one. So you could have one implementing, or you could require W to implement multiple traits,
Yes.
right?
Yes. You can have. Yeah. Let's make an example yeah. Let's go with the trait a bit further. Yes, you can do that. Syntax is just if your type depend on multiple traits, you just add them like this plus the next trait and so on and so on. Let's make an example. So Rust come up with some trait of its own that you can implement. For example, if here we have Welsh and we want to print Welsh, we can do it. I think I can do it like this. Print. Yes, there's a new syntax essentially. I think it's got like this. Oh, just Welsh. We can just pass it like this. Cargo built example. Okay, let's do that. What is say that Welsh cannot be formatted with the default formatter. The trait standard format display is not implemented. Okay. In format string, you may be able to use that or that one instead. So when you have a custom structure, you will refuse to print it because you need to provide your own formatted structure, unless you do two things. Yeah, you can use that like this. And here I say you can print your structure. It's a bit like Python has the same concept. You can print a custom structure in a pretty format or in a debug mode. Right? So that means that Rust can provide a default formatting of your structure to print information about it. But you have to be explicit about it. So that means you need to implement, well, as he said, it doesn't implement the debug trait. So a bit like we did with application, we could go along and say implement debug for Welsh and do an implementation ourselves. But Rust comes from default, and you can ask him to apply default trait to your structure by doing that. Derive the debug trait for me. So what this little attribute that we add to Welsh, I think Python we call that decorator, is going to do implement debug for Welsh for me instead of having me writing like that. So now if I try to print it, yes, almost there. It didn't work because for a structure to be able to print it with the default debug mode, every variable needs to implement the trait debug. So all the primitive type, like integer, floating point, vector, etc., implement the debug mode, but Windows doesn't do that. Okay. So when we define our structure, we need to have it also deriving the debug trait. Well, that's because it's going to be used when we print Welsh. So if I try to do that, it compiles. Let's try to run it. So now it compiled, but you see, it compiled every piece of every data, which is not very very useful. So it's good in debug mode, but so what you need to do is to define your own trait. So in that case, you will define your own trait, and there's a trait for printing that Rust defined already. So you just need to implement it. To implement display for Welsh. W. Need to define all the properties of W. Yes. Oh, it doesn't what it said here. Cannot define. Import. Okay, let's import. Okay, so you see what it does. He has added. He has imported the display trait in the workspace here, and now we're going to should be able to implement it. Yes. So this here's a default method that we need to re-implement. So and the way to do it is to do it somehow like this. You have this write function f, and we can put number of segments. Put that here like that. And we will self dot end segment. Okay. Forgot to add window here. We have to repeat the trait each time we have an implementation. So you see Christophe, there's an implementation block for each trait.
Mm-hmm.
Okay, it compile. So now, if we want to print Welsh, no longer in debug mode, but really using the nice printing function we have, we just need to remove the question mark. The question mark is to say debugging, printing in debug mode. Let's try to run that. Yeah, that works. Okay.
When you implement the display for Welsh, what's the lowercase a for? Is that a lifetime or something?
Yes, everything you define as placeholder, including lifetime, has to be repeated in the implementation.
Okay.
Right? You have to repeat that. It's just a part of the definition of window. It's come with because it's part of the definition of Welsh. So
Okay.
Welsh. You need to repeat it.
So if you change the implementation of Welsh where it now has 2 lifetimes or something, then you have to go everywhere you use Welsh to.
Yes.
Okay. There's no easy way to do it?
No. I'm aware of. So that's about it. And what I wanted to say is you could have also, oops, if we wanted to add a line for displaying, we're doing something. I'm not going to explain what I'm doing now, but otherwise you won't like it. Where we display you print some window information directly here by having a window. Here is going to complain because window doesn't implement the trait display. So in that case, it's where I was going. You need to. It's where you can add another trait on window stuff.
Mm-hmm.
So, oh yeah, that's interesting. So you can add it here. Oops. Yeah. Okay. But that's going to imply that I have to do plus display everywhere. So I have to do it here and here. That's compiled now. But in fact, I don't need the functionality of display when I really use Welsh. I just need it for the printing. So you can just, I think that will work too. And no, it doesn't work. Okay, okay. Okay. I thought it would, but no. Okay, so you need to repeat it. That's interesting. You see? So you can add multiple constraints, multiple traits on your. But now in your application, it won't work because now you expect one to also have a display trait. So you need to also now add the display. Oops.
Could you change your window trait to make it so that it also implements display?
Implement display on window. I don't think so. I don't think so. Because you need to know the type of the function you're going to print, and you don't know that yet. So you need to implement that really in the application.
When you defined one, the only way that Rust knows that one implements window is because you implemented the functions, right? It's not.
Yes.
Okay.
And now that I have, yes, you need to implement it like here. You meaning here?
Mm-hmm.
Yes, you need to do that here. You just need to import it in order to trait display in the workspace here too. Okay, now it's compiling, you see. So there's kind of, so the compiler will force you to go through all that, do all this check for you, and now it printed. You see, let me do a bit, okay, write line by line instead of one or the other.
Is there a default? So what if you wanted to save a structure as a file? Is there a default sort of trait?
No, there's nothing coming in the Rust library, standard library to do that. Okay. You need to look at third-party crate and look at ways to do that. There's several, but Rust doesn't provide a mechanism to do that. We need to go to lib.rs, for example,
Mm-hmm.
and look for that. So the thing which, if you only lived and remain, if you want your data to remain only in the Rust ecosystem, you don't want to share it with Python, MATLAB, whatever. You just want to save your structure at some point and reload it in Rust. You can something I like to use that case is called beancode. It's really a serialization, deserialization tool for Rust structure into bytes, into a file, and you can. That's pretty nice. But if you want to go back and forth with Python, you can use something called SerDPicker for that. With MATLAB, it's pretty limited what we can do so far right now.
Mm-hmm.
Okay, that will be all for today. We covered the generic and traits today. I hope that start to make a bit more sense. It's a very powerful concept, but at least for me, it was different from what I'm used for, what I'm used to use in other programming language. So that's it took me some time to get used to it. You have any question? Or we can just stop here for today.
Yes.
Okay. I saw Jordi join us for the first time. Hi, Jordi.
Yeah, I was interested on Rust. I couldn't join the previous meetings because I was in Tucson with M1 test, and it was full day.
So I recorded the previous session on YouTube. I don't know
Oh, if you can send me the link.
Yes,
Yeah.
I will send you. Except the second session where I forgot to record, but otherwise. Okay.